Welcome to Unit 7. We are going to study conic sections in this section. There are 4 types of conic sections that are of interest to us. So first we're going to define some conic sections, and then we will look at each of those 4 conic sections in detail, the 4 that we're going to study. First we're going to study circles, so that's what this video will consist of. Let's take a look at our definition of conic sections. A conic section is formed when a right circular cone with 2 parts is intersected by a plane. So we have a picture here of our 4 types of conic sections. If the plane intersects across one of the cones but doesn't touch the other one, then you get a parabola, actually. If it intersects straight across one of the cones, such that that plane is parallel to the base of that cone, you'll get a circle. If it intersects across one of the cones where, but not parallel, then you will get an ellipse. And if it's perpendicular to the base of the cone and intersects both of those cones, you will get a hyperbola. Those are our 4 types of conic sections. Geometrically, these conic sections result from these intersections of the plane and this what we call double napped cone. Algebraically, conic sections are going to be defined with a locus of points. That's a fancy mathematical term for the set of all points that satisfy a given condition. We will talk about algebraically what these are as we study each of the different conic sections. One thing that's important about these conic sections, one thing that's important to recognize is that most of them are not going to be functions. We'll see that as we get into the study of them more. The parabola is the only one that can be a function, and sometimes it's not, depending upon what that parabola looks like. Here's a hint. We're going to look at parabolas that open sideways instead of up or down. So that would not be a function. But there's value in studying conic sections because of some of the applications of them. We are going to see that as we study each section. I have a portion of it that describes where these show up in the real physical world. Let's talk first about circles. I know we're kind of going out of order here. We're going to do the circle, the ellipse, the hyperbola, and then the parabola. So first circles, that will be the first conic section we study. Remember we set up here that algebraically conic sections are defined to be a locus of points that satisfy a given condition. So that's how we're going to study each of these. Before we can really study circles, we do have to determine the distance between 2 points. We have to determine the midpoint of a line segment, and that will allow us to find the equation of a circle. First, let's start with that definition, that algebraic definition. It's the set of all points that are equidistant from a fixed point. That fixed point is called the center here. So I'm always thinking about, like, if I put a nail in some place with a string and had a pencil attached to that string and just went all the way around with that nail, that fixed point, that's going to be the circle, right? Hopefully y'all are pretty familiar with circles. So we're going to study this in a little bit different approach than what you may have seen before. The distance between 2 points, x1, y1, and x2, y2, can be found using basically the Pythagorean theorem, right? If we're looking for D here, this distance, whatever it is, that's the change in x. So it's x2 minus x1. This distance is y2 minus y1. That's the change in the y's. By the Pythagorean theorem, x2 minus x1 squared plus y2 minus y1 squared will equal d squared. Thus, the distance, just the d between those 2 points, will be the square root of the the left-hand side of this. One thing that is important to recognize is the order of the subtraction here doesn't really matter because we are squaring the number. So sometimes you'll see the distance formula written as x1 minus x2 squared plus y1 minus y2 squared equaling d. It doesn't really matter. One, the subscripts just distinguish between the points. But when you square, if this distance is 6, if you square 6 or negative 6, you still get 36, so it doesn't really matter. But this, I think, would be a more common way to see the distance formula written, like if you're looking online at another resource or in a textbook or something. Okay, let's do it. Let's find the distance between these 2 points. We could plot them if we wanted to. 3, 2 is here. Negative 4, 1 is here. So we're looking for this distance, whatever that is. It will be the square root of, we have to subtract the x values, 3 minus negative 4, and square it. Subtract the y values, 2 minus 1, and square that. That is the square root of 7 squared is 49, plus 1 squared is 1. Square root of 50. Most commonly, we would see that written as 5 root 2. That is the distance between those 2 points. As far as the midpoint between 2 points, it's basically the average of the x-coordinates and the average of the y-coordinates. So the idea here is that the midpoint is going to be halfway in between these two. So that's going to be the average of those. And then halfway in between those two is the average of the y values. So x1 plus x2 over 2 is how you find an average, right, of those 2 values. y1 plus y2 over 2. We're going to find the midpoint of these same 2 points. 3 plus negative 4 over 2 will be the x-coordinate. 2 plus 1 over 2 will be the y-coordinate. Negative 1/2, 3/2. And I'm going to go back to my picture that I found here and just make sure that that makes sense. Negative 1/2, 3/2 would be, that's pretty close, right? I mean, my picture's not the greatest here because I was kind of rough sketching it, but that makes sense there. Okay. The reason that we want to be able to find the distance and the midpoint is going to help us with finding the equation of a circle. Not finding the equation of a circle. Well, finding the equation of a circle, not the formula for it, but finding some things about it. I'll show you that in an example here. Remember we said that the standard form of the equation of a circle with center, or here we're saying that the standard form of the equation of a circle with center HK and radius R is this formula. The question becomes why? Remember that we said, let's suppose we're at some point HK here. We said every point on the circle is equal to the same distance away, right? So this distance is R, whatever that circle is, right? Okay, so any point out here, let's call that some point XY. That would be true of, a point down here is going to have some coordinates x, y, right? What we know using that distance formula is that if this is hk, every point on the circle is going to be have distance equal to r between hk and whatever point xy, right? X point is general to describe any point on the circle. Using that distance formula, or the Pythagorean theorem, however you want to see it, r, that distance between these 2 points, will be x minus h squared plus y minus k squared, and the square root of that. Squaring both sides of that gives me that formula that you see in the box above. X minus h squared plus y minus k squared. That's where the equation of a circle comes from, going back to the definition that every point on the circle is that same fixed distance r away from the center, which we're calling hk here. Find the equation of the circle with center 4, 2, and radius 5. Excuse me. I'm going to write the standard form of the equation of a circle down. We actually saw that back in a previous unit when we were looking at systems of nonlinear equations and inequalities. I showed it to you there because it kind of showed up in some of those examples, but here's sort of the why. Let's plug in what we know. Center of 4, 2 means h is 4 and k is 2. So we get x minus 4 squared plus y minus 2 squared is equal to 25. Here we're going the other way, find the center and radius of this circle. Well, the center has x coordinate of 0 because there's nothing, this is like x minus 0 squared, right? Y coordinate of negative 2 because it's the opposite, that minus k in the formula. And then the radius would be 3 because r squared is equal to 9 here. Radius is always positive, so even if we square root that, we get the plus minus. You can't really have a negative radius. The reason that we looked at the midpoint and distance formula before, well, we needed the distance formula to develop the equation of a circle, but we also need it on a problem like this. We are looking at a circle that has these 2 points as endpoints of one diameter. We had this picture before, right? These are the same points that we looked at before where we found the distance between them to be the square root of 50 or 5 root 2. And we found the midpoint between them to be negative 1/2, 3/2. The reason that that matters is because that tells us the center of the circle and the diameter of the circle, right? So let me draw this picture again. 3, 2 is here. Negative 4, 1 is here. If these are endpoints of a diameter, that means we have a circle here, right? The center, because that's a diameter always goes through the center is the midpoint. This is the center of the circle. This is the diameter of the circle. because that's the distance between those 2 points, that tells me the radius is half of that. 5/2 root 2, divide that by 2, and the center is -1/2 3/2. So now I can write my equation. X, it'll be plus 1/2 squared plus y minus 3/2 squared will equal 5/2 root 2 squared. Let's clean that up a little bit. Just that right-hand side, what is that? 25/4 times 2 would be 25/2. Okay. That's it. That's the value in that distance formula and the midpoint formula in the context of looking at circles. One thing we do need to look at is, what if the equation that you're given is not written in that standard form? It's not written as x minus h squared plus y minus k squared equals r squared. That is the most valuable form to see a circle in, because you can easily read off the center and the radius. This is indeed a circle, what we see here. The problem is it's not written in this form, and so we can't really, it's hard to see what the circle, center, and radius are. The way we go from this form to this form is completing the square. I'm going to write the x terms together and leave myself a little space to complete the square in. I'm going to put the y terms together, leave myself a little space to complete the square in, and I'm going to add 4 to both sides. When I complete the square on this x squared plus 12x, I take the 12, that's my b, divide it by 2, and square it. That's 6 squared, or 36. If I add 36 to the left side of the equation, I have to add it to the right side of the equation. Now let's complete the square on the y terms. -6/2 squared is -3 squared, or 9. Plus 9 plus 9. Factoring the first perfect square trinomial here gives me x plus 6 quantity squared. This one will be x minus 3 quantity squared equals, what is that, 49. That is the standard form of a circle. From it, we can read right off the radius, or I'm sorry, the center, -6, 3, and the radius is 7, the square root of 49. The way I know this is a circle is because I have both x squared and y squared with their coefficients being equal and the same sign. They both have to be positive. If they're both negative, I can divide by a -1, and that's okay, right? That will still get me to be able to be in this form. But those coefficients have to be the same. You can't have a 2 on the x squared and a 3 on the y squared. You won't ever be able to get 1 here and here. If you have 2 on both, you can divide both sides of the equation by 2 and get to that form. We'll see what happens if the coefficients on x squared and y squared are both different.